Hello and welcome back. This video is meant to support the notes that we are taking on simple harmonic motion. Let's begin. Section 19.1, Observations of Vibrational Motion. Explain vibrational motion. Vibrational motion, simply put, is any back and forth motion. It is synonymous with periodic motion, which from this point out I'm going to abbreviate as PM. What is the equilibrium position of an object that has vibrational motion? Equilibrium position is the place where an object will not move when initially put there. The object, when in vibrational motion, will pass back and forth on opposite and equal sides of this equilibrium position. What does a restoring force do? What is the restoring force in observational experiment 19.1? You are going to want to turn to the electronic textbook, page 696, to access observational experiment 19.1. But what does a restoring force do? Restoring forces always try to get the object to move and be restored back towards the equilibrium position. Again, please take time to seek out pages 696 for observational experiment 19.1 and page 698 in observational experiment 19.2. We will be going over these observational experiments in next week's class. That would be Monday for period 1, and that would be Tuesday for period 6. What is amplitude? Amplitude of a vibration is the maximum displacement of the object from its equilibrium position. So if X is the displacement of an object, then the amplitude, which is written with a capital letter A, is equal to X max. Section 19.2, period and frequency. Explain period. Period is the time it takes to complete one vibration. Okay, a synonym for vibration, of course, would be cycles, oscillations, waves. Now, another way we could describe it is the period, which uses the variable capital T, units are seconds. The period is the number of seconds for each cycle or each vibration. Explain frequency. Frequency is the number of vibrations that occur each second. The unit for frequency, the variable, for frequency is a lowercase f, and the unit is abbreviated Hz, which stands for hertz. Period is the time it takes to do one vibration, one complete cycle. Frequency is the number of cycles each second. As you can see, these are reciprocal concepts. Therefore, if we want to calculate the period if given the frequency, we would simply take the inverse of the frequency to get the period. Or we could take the inverse of the period to get the frequency. We will review the test your understanding portion here in next week's class. Turn in your notes to page 3. And let's briefly review some of the concepts that we went over in last class. To begin with, basic periodic motion, as I mentioned earlier, is any back and forth motion. Simple harmonic motion, which we're going to abbreviate SHM, is a more specific level of back and forth motion. It's back and forth motion in which the acceleration is related to the negative of the displacement. Now, what does this have to do with? Well, if you recall, objects in simple harmonic motion are always undergoing a restoring force. That's what F stands for. It's a restoring force. And it's proportional to the negative of the displacement. Again, why is restoring force negative? Because as an object is moving one way, the spring or pendulum, whichever the oscillator is, wants to restore itself back to an equilibrium position. In other words, opposite to the direction of displacement. But you might also recall that force is equal to ma, which means that whichever way the force is going, in this case the force is negative, the acceleration is also negative. And acceleration, force equals ma, that means acceleration equals negative kx over m. We'll come back to this one a little bit later. But what it serves to remind us is acceleration is related to the negative of the displacement. That is a key feature in defining simple harmonic motion. Recall that at the amplitude position, displacement is a maximum. At the amplitude position, your object stops, changes direction, and goes the other way. Therefore, velocity is 0 because it has to stop in order to change direction. If velocity is 0, kinetic energy is also 0 because kinetic energy is 1/2 times mass times velocity squared. Force is a maximum because force equals negative kx, and if x is a maximum, force is a maximum. If force is a maximum, acceleration is a maximum. That is why we see maximum applied in all three of those situations. Now, why are force and acceleration negative maximum? Because, again, of the concept of restoring force, always wants to restore an object back to the equilibrium position opposite the direction of motion. Since that position, since that displacement is a maximum, potential energy is also a maximum. Now, if we look at the equilibrium position, which is the midpoint of the oscillation, it's the midpoint of the distance to either amplitude, we would call this a displacement of 0. Okay? It is the place where you will also have no net force and thus no acceleration. It is the place where you will have maximum velocity and thus maximum kinetic energy. If you have maximum kinetic energy, by law of conservation of energy principle, you should have converted all of it to kinetic energy and therefore should have no more potential energy. Let's take a look at position, velocity, acceleration time graphs, potential energy, kinetic energy, and total energy time graphs. As you can see in this animation, there is a mass on the end of the spring that vibrates up and down, north and south of an equilibrium position right in the middle. Right now it's at the upper amplitude. Right now it's at the lower amplitude. Right now it's passing through equilibrium. And so what we're going to do is we're going to examine each of the qualities that can be analyzed with this. Number one, This animation is showing an object of the vertically oscillating spring. Displacement is the blue graph. Velocity is the green graph. Acceleration is the red graph. Potential energy is the light blue graph. Kinetic energy is the yellow graph. And total energy is the pink graph. Note that when velocity is negative, look at when velocity has a negative slope. Okay, this would be the negative slope of displacement. So if we look at the blue x graph from 0 to 2 seconds and from 4 to 6 seconds, you see those are negative slopes. Therefore, during this entire time interval, you have negative velocity below the graph. Note that when velocity is positive, when displacement has positive slopes. Notice in the blue graph, from 2 to 4 seconds and from 6 to 8 seconds have positive slopes, corresponding to positive velocity in the velocity green graph. Now let's take a look at the velocity and the acceleration. If we look at the green velocity graph, you'll notice that between 1 and 3 seconds of the green graph, it is sloped upward and positive. And from 5 to 7 seconds, it is also sloped upward and positive. Those correspond to positive acceleration. And therefore, you should have positive acceleration in the red graph below during those same time intervals. You'll also notice that from 3 to 5 seconds of the green graph, the velocity graph, you have a negative slope. And this, of course, corresponds to a negative acceleration on the red graph below. Also note that acceleration is the opposite of displacement. Remember, for simple harmonic motion to be true, acceleration is related to the opposite of the displacement, or the negative of the displacement. So you should see that the acceleration graph should be a flipped or reflected image of the displacement graph. However, the amplitudes will not be the same necessarily. We'll explain that one a little bit more later. However, the shape of the graph will be flipped. Now, if you're asking to draw momentum versus time, it'll look exactly like velocity versus time because momentum is mass times velocity. The amplitude will be a little larger because you're multiplying the mass times the velocity, but the shape of the graph will be the same. If you are asked to draw a net force versus time graph, it would look like the acceleration graph because force is proportional to acceleration. Remember, F equals ma. Again, the amplitude or the height of the graph would be larger because you're multiplying mass times acceleration. But the shape of the force versus time graph would be the same shape as the acceleration versus time graph. If you're asked to draw a momentum versus time graph, again, it will look like the velocity time graph. And again, a force versus time graph will look like the acceleration versus time graph. Now let's look at the energy graphs. The light blue graph is potential energy. Now, remember, kinetic energy cannot be negative. If we go K equals 1/2 mv squared, the mass can't be negative, and by squaring velocity, it makes the whole thing positive. So there are situations where potential energy can be positive, but this is not one of them since U equals 1/2 kx squared. The spring constant is K, and that must be positive. And x cannot be negative because you square x, which is the displacement from equilibrium. Therefore, spring or elastic potential energy will be positive. The potential energy is going to be the highest at the endpoints where the displacement. So wherever you have positive displacement, you will have maximum potential energy. You'll notice that at 2 and 6 seconds, the negative displacement becomes positive potential energy, because again, we cannot have negative potential energy. The kinetic energy graph also will be the highest when velocity is a maximum. You'll notice at 1 second and 5 seconds, the negative maximum velocity have become positive kinetic energy, because again, kinetic energy cannot be negative. But whenever you have a maximum, in other words, the amplitude of a velocity time graph, that'll be the same amplitude of a kinetic energy versus time graph. And the total energy in the pink graph should remain constant all the way across the positive amplitude of either the kinetic or potential energy graphs. So for an object to exhibit simple harmonic motion, these statements must be true about the motion. Number 1, the force acting is linearly proportional to displacement. What does that mean? It means if you draw a force versus displacement graph, it represents a straight line right through the origin. Number 2, the period is independent of the amplitude. What does that mean? It means however far you pull back the object, whether it's the mass on the spring or a pendulum, however far you pull back the object from equilibrium will not affect the time it takes to go back and forth. Now, for a pendulum, that's a special case between 0 degrees and a maximum of 15 degrees from that vertical position. More on that later. And 3, the motion itself is represented as a sine wave. Okay? Again, what makes simple harmonic motion possible? The acceleration is proportional to the negative of the displacement. Why is this? Because all objects in simple harmonic motion undergo a restoring force. Okay, so how do we go from position time graphs to velocity time graphs to acceleration time graphs? I'm going to show you a few key features that will help you. 1, your graphs and your functions will alternate between sine and cosine functions. Okay, we are now beginning to look at the functions or the equations that match these sine and cosine graphs. Number 2, we're going to increase by 1 factor of omega each time. Now, this is the first time we're bringing up omega, so we'll a little bit more to come on what that is. And sine, if your function is going from sine to cosine, the sine will stay the same. Meaning if it's positive, it will stay positive. If it's a negative, it will stay negative. If we are switching from cosine to sine, the sign changes. So if we're negative, it switches to positive. If it's positive, it switches to negative. So I'm going to see these particular rules applied. Now, for those of you who have a little bit of introduction to calculus, this would be as simple as taking a cosine function, let's say cosine of t, and taking the derivative of that function to get v. By taking the derivative of this function, you not only have to derive a cosine function, you also have to use chain rule. So if you understand how to do that, those mathematical laws are implied in these descriptions I have laid out right here. If you are not at that level of math, then you're going to use these descriptions I've laid out right here. A little bit more on this concept of omega. Omega is represented by this lowercase w. It's not a w, it's the Greek letter omega. Kind of looks like this. All Greek letters in the alphabet have an upper and lower case. This is the lowercase omega. And it stands for the angular frequency. Now, when we get to rotating objects, we're going to rename it as the angular velocity. But for now, it's the angular frequency. A little bit more to come on that. The angular frequency relates to the total rotation or the total completion of a cycle. So how about we represent our cycle of back and forth motion as very similar to what we would see in a circle. So if I were to, let's say, have an object attached to a rope, and that object were to be making a vertical circle like this, and on top of that, we were shining a light right on top of that whole thing, what would we notice? We would notice a shadow at the very bottom, a shadow of the ball right here. We would notice a shadow of the string. And we would notice this shadow move from one side to the other side, back and forth like that. So this is the oscillatory motion. However, ladies and gentlemen, you can make a connection between oscillatory motion and the periodic motion of an object actually moving in a circle. So, let's review a couple things. Number one, the full circle makes 360 degrees of rotation. Now, another mathematical way to describe a rotation would be a radian. So angles are either measured in degrees, which many of you are familiar with, or radians. We are going to be taking a look at that. 360 degrees happens to be equivalent to 2 pi radians. So one full revolution is equal to 2 pi radians. So if we go back to the angular frequency relates to the angular velocity. Now, velocity, ladies and gentlemen, would be distance over time. Therefore, if we take the angular displacement, which is 2 pi radians, over the time it takes to do one revolution of that circle, otherwise known as the period, we get a relationship between omega, the angular frequency, and time. Now recall, ladies and gentlemen, that 1 over the period is the same as the frequency. So you could rewrite this as 2 pi times the frequency. So we have a couple relationships for angular velocity and angular frequency. We're going to be using these, okay, as we go along. It's important to note that whatever the period is, if the period stays constant in an oscillation, the frequency obviously is going to stay constant, and thus the angular frequency will remain constant. More to come next week when we review this more in detail. What is the general equation for the position versus time graph? Well, for a position versus time graph, we can write it as follows. X equals A times the cosine of omega t. Now remember, omega is this thing here of 1 full revolution times the frequency of oscillation, known as the angular frequency, or 1 full revolution divided by the time it takes to do that revolution. So that's what omega represents right there. Time is the variable, so this is position as a function of time. Okay, and that's what we're doing here, position as a function of time. However, let's also relate this to the fact that you can also have velocity and acceleration as a function of time too. Please note that this term here in the front, this is the amplitude, or x max. Now, to get the velocity function, let's use the steps we have here to figure that out. Velocity as a function of time. Well, here we go. The velocity function, the first thing we're going to do is we're going to alternate between sine and cosine. So if we alternate between sine and cosine, and we're starting with a cosine function, that must mean that this next one is a sine function. And since the period is not changing just because we're describing a velocity instead of a position function, the angular frequency is the same as well. So in other words, if x is proportional to omega t, velocity is also proportional to omega t. Okay, the only thing we did differently is we replaced and alternated from cosine to sine. Now, what's the next one? If we are going from cosine, if we're switching from cosine to sine, you need to change the sign, which means we need to go from positive to negative. Let's place a negative out in front. The next thing we need is part 2. You're going to increase by 1 factor of omega each time. Well, you might be saying to yourself, well, how could I increase by 1 factor of omega when there's no omega there? Well, there actually is. If you were to rewrite this, it would be x equals a omega to the 0 power times the cosine of omega t. Remember, ladies and gentlemen, anything written to the 0 power is 1, and a times 1 is a. So this would be omega to the 0 power. Therefore, we would write this as a times omega. We're increasing by 1 factor of omega. In other words, omega to the 1st power. Okay, and that is our velocity as a function of time. Now, to get the acceleration function, you're going to do the same thing. Repeat the steps. We're going to alternate between sine and cosine. So acceleration is going to go from sine back to cosine of omega t. If you're going from sine to cosine, the sign stays the same. So since it's negative, it's going to stay negative. And lastly, we're going to increase by 1 more factor of omega. So if we are a omega to the 1st power, this now becomes a omega to the 2nd power. Okay, now a couple things to note. If this is x max, then that means this term out in front here, a omega, that, ladies and gentlemen, is v max. That would be the amplitude. Anything out in front of a sine or a cosine function is the amplitude of the wave, the amplitude of the graph, how high the graph goes. That makes this term v max. A is x max, and it makes this term a omega squared a max, or maximum acceleration. So let's summarize this below. Amplitude is x max. Velocity let me write that the other way. X max is amplitude. V max is amplitude times omega. And A max is amplitude times omega squared. You're going to need these from time to time. Okay, so now let's begin to derive the equation that represents the period of a mass oscillating at the end of the spring. To do this, we're going to begin with the basics. Recall that omega is equal to 2 pi over the period. Remember, angular distance over the time for one cycle. Now, what we could do is we could switch this and we get a very generic equation for period. The period of any oscillator, it doesn't matter what it is, mass, spring system, pendulum, you name it. The period of any simple harmonic motion oscillator is 2 pi over omega. Let's put a box around that because that's going to become handy from time to time. Now we're going to use this to derive the next equation. Okay, so follow along with me, guys. Also recall that net force is equal to kx because objects in simple harmonic motion undergo a restoring force that acts opposite to displacement. Now, if that's true, then net force also equals ma, and thus negative kx will equal ma, which means A is equal to negative k over m. But also, A, if you look above, is also, at least if it's a maximum, is equal to amplitude times omega squared. So now with that said, we can make a couple things happen. If this represents the maximum acceleration, then this x becomes amplitude as well. Meaning, I can put those together. Now, I'm only focusing on the absolute value of this, so I'm only focusing on the relationship here, not so much the negative, okay? So we're going to put these together, and if A max equals A max, then K A over M equals A times omega squared. A couple of things happen. Cancels, cancels. And we have our next very useful equation. Omega squared equals K over M. Or omega equals the square root of K over M. I would write these down. Those are very handy equations to know. Lastly, we're going to put it all together. Period is 2 pi over omega. And yet omega is the square root 2 pi over the square root of K over M. Now I can rewrite this. When I divide a fraction by a fraction, I can always rewrite this as T is equal to 2 pi times the square root of M over K, meaning if I multiply by the reciprocal of that fraction, that's the same thing as dividing. And that, ladies and gentlemen, is the period of a mass spring system, using a couple helpful equations along the way. All right, again, recall that net force equals MA, but that this net force is a restoring force for a simple harmonic motion oscillator. Thus, negative kx equals ma. Okay. Let's take a look at this test your understanding below. Read along with me, please. Suppose that a vibrating object can be described by the position versus time graph of x equals negative 0.32 sine of 7.31 t, where x is measured in meters and time is seconds. The mass is 6.2 kilograms. What is the spring constant? So we're looking for K. All right? Let's figure out how to do this. One, let's write the equation down. Okay, number two, identify the parts. This would be your amplitude. This would be your omega. So omega is equal to 7.31. Now the units for omega are rather unique. The units for velocity are meters per second. The units for omega are radians per second. Rad, R-A-D, is short for radians. Now, recall that omega is equal to the square root of m over k. That would allow you to solve for k. Or you could have written omega squared equals m over k. In other words, square both sides. K, sorry, I miswrote that. K over m. So if we solve this equation for K, we have to multiply both sides by the mass. So K would be equal to the mass times omega squared, which would be 6.2 kilograms times 7.31 radians per second. Don't forget to square it. We put that in our calculator. 7.31 squared times 6.2 is approximately 331 newtons per meter for the spring constant. Now, section 19.5, energy of vibrational motion. Give three equations that express the total energy of objects experiencing simple harmonic motion. Well, when you're at equilibrium, it's quite simple. Velocity is a max. X equals 0. Therefore, the total energy is really just the kinetic energy, or 1/2 mv squared. At amplitude, it's the opposite. Velocity is 0, and x is a maximum. Therefore, your total energy is now only potential energy, 1/2 kx squared. But instead of x, notice we're writing a, because remember, a is x max. And then lastly, the total energy, somewhere anywhere in between, would be the sum of 1/2 mv squared and 1/2 kx squared. Okay, what is the equation that gives the period of a pendulum? Now, similarly, there are some similarities to this, and I will derive this at a later time, but the period of a pendulum is 2 pi times the square root of L over G, meaning it depends on the length of the pendulum and the acceleration due to gravity. Now, if you were to rewrite this as 2 pi over the square root of G over L, because remember, Dividing by a fraction is multiplying by the reciprocal, right? Then what that would tell you is this is 2 pi over omega. Remember this equation from earlier? Well, that tells you that omega can also be written in terms of a pendulum. So omega for a pendulum is the square root of g over L. Or you could say omega squared is g over L. So you have omega for a spring, which involves spring constant and mass, and you have omega for a simple pendulum, which involves the acceleration due to gravity and the length. We will take a look at this example in class. Go ahead and turn to the last page 6, section 19.8, including friction in vibrational motion. Sketch a position versus time for a function in simple harmonic motion that is not subject to friction. Well, this simply put would be one in which the amplitude remains constant. So make a position time graph as a sideways T. Position in meters, time in seconds. We're going to go ahead and mark off a mark here for T. That's one completion of a cycle, meaning T means period, capital T. Go twice as far. That's 2T. That means 2 cycles. We'll go T over 2. That's half a cycle. 3T over 2. That's a cycle and a half. So we have the ability to draw 2 full cycles in this picture. What I want you to do is draw some dashed lines across the top and across the bottom to represent the amplitude, how high the wave can go. Let's say the wave is, starting with a cosine graph. Cosine graphs always start or pass through amplitude. Sine graphs always pass through the origin. And so graph might look like this. You'll notice, ladies and gentlemen, the graph always returns to that highest and lowest point, meaning the amplitude is kept constant when friction is not a part of the problem. So how does the problem begin to look when friction is part of the problem? Well, the amplitude will then diminish with time. So again, draw your position versus time graph. X in meters, time in seconds. Again, period T, 2T, half a period, 1 period and a half, and so on. What you'll notice is that the amplitude is going to diminish with time. In other words, the amplitude is going to get smaller and smaller and smaller. This is seen with dampening devices. Shock absorbers, for an example, are meant to absorb the energy and thus prevent the oscillation, meaning we go over a pothole with good shock absorbers in a car, we don't feel the oscillation as much. It doesn't transfer, the energy doesn't transfer to the occupants in the car. Therefore, it diminishes with time. And the same equation would look like this. Graph, that is, not equation, I misspoke. But you can see how the amplitude is decreasing as time goes on. Section 19.9, vibrational motion with an external driving force. Explain resonance. Resonance is essentially a forced vibration by which the environment applies a force onto the system. The environment, something outside the system, essentially does positive work on the system. So over time, the environment does positive work on the system and thus increases the system's total energy. And if you increase the total energy, you increase the amplitude of these vibrations. The conditions necessary for resonance would be the natural frequencies of the environment and the system. They have to be close, if not matching. And there must be some mechanism that exists that allows something in the environment to do positive work on the system. Let's give you an example. Say you have an opera singer who can raise his or her voice to a very high level. And if you're able to do so, sometimes singers who can sing with a very high pitch can get wine glasses to break. How does this happen? Well, the opera singer is creating sound waves, and the sound waves themselves are transferring energy from the vocal cords of the singer out into the environment. Now, the opera singer becomes the environment, and the opera singer begins to do work to vibrate the glass molecules that make up the wine glass. And over time, the frequency matches. So if the opera singer keeps up that same frequency, it begins to match that of the vibrating nature of the wine glass. And if this continues, the amplitude only increases to the point where the wine glass can no longer sustain the integrity of the structure, and thus it breaks. The same can be applied to a child on a swing. Let's take a look. An external force is applied by a person. The person would be the environment. Onto the child swing earth system, to be more specific. The external force, meaning the person, does positive work on the vibrating swing. So, for instance, if a parent is pushing a swing and wants to make the child go higher, you push in the direction of the swing. So if the child is swinging down, you push down. You're doing positive work. You increase the energy of the child earth swing system. What does the child do? The child thus swings higher. You've put in more work, you've increased the energy of the system, and therefore the amplitude increases and the child swings higher. There are many examples of resonance. I would encourage you to look up videos of the Tacoma Narrows Bridge. This is an engineering failure that occurred back in 1930 of a bridge that was outside of Tacoma, Washington. There was video taken of this, late 1930s. This bridge was built after the Golden Gate Bridge, however, was an engineering failure compared to that of the Golden Gate Bridge. I'd like you to take a moment to look this up, look up videos on YouTube, and take a look at the disaster that was a result of this engineering failure and an example of resonance.